right, let's look at complex numbers. Earlier in the year, we talked about the complex number system and that it is made up of real and imaginary numbers. And so today we want to look at imaginary numbers. An imaginary number I is the square root of -1. You can't actually take the square root of a negative number, so that is an imaginary value. If you square both sides of that equation, you get I squared is equal to -1. So when I'm working with an imaginary number, we're going to write its standard form as a plus bi, where a is the real part and bi is the imaginary part. If you had a number that only had the imaginary part, like 3i, that's called a pure imaginary number. Now, the equality of complex numbers says that if you have two complex numbers, a plus bi and c plus di, written in standard form that are equal to each other, they'll be equal if and only if a is equal to c, real part equals real part, and b is equal to d, imaginary part equals imaginary part. So in our example, when they tell us a plus bi is equal to 4 minus 3i, then we know that a has to be equal to 4 and b has to be equal to -3. All right, let's look at some of the operations that we can do with complex numbers, starting with addition and subtraction. When you're adding complex numbers, it is very much like when you're adding variables. Now, I is not a variable. It's the square root of -1, but if I thought of it like I do x, if I had 3 plus 2x and 4 minus 3x, if I were going to go through and combine those, I can take out my parentheses here because this is addition without changing anything, and I would combine my like terms of 3 and 4. If I combine 2i and -3i like I would 2x and -3x, when you have like terms, they have to have the same exponent raised to the same variable raised to the same exponent. We combine our coefficients and then we keep that variable and exponent the same. We're going to do something similar here. If I'm adding 2 i's with a -3 i's, I'm going to combine the 2 and -3 to get -1, and then I'm going to keep the I the same. All right, if I'm subtracting, don't forget that you must distribute that negative to everything in that second set of parentheses. So it would be -4 and then minus a -3i plus 3i. So if we again go through and combine like terms, 3 minus 4 would give us -1, and then 2i plus 3i would give us 5i. All right, what about multiplication of imaginary numbers? If we had x times -3x, we'd get -3x squared. If I have I times -3i, I'm going to get -3i squared. However, remember that I squared equals -1? Well, then I could replace I squared with -1. So -3 times -1 would give us a +3. Now, each of these things that we've done so far by hand, we could do on our calculator. So grab your graphing calculator if you would, please. We're going to need to change a setting on our calculator to be able to do this. So if you'll go to mode and scroll down, right now you are probably in real mode. We want to switch over to a plus bi mode and hit enter. All right, then I'm going to quit out of that and go back to my main screen. So if we go back to those same problems that we did just a minute ago, we had 3 plus 2i, and where you get your I is right above your decimal, so you're going to do second decimal to get your I. We had 3 plus 2i plus 4 minus 3i. So 4 minus 3i. And you'll notice that gives us that same 7 minus I that we got when we did this together. I'm going to hit second enter to get my calculator to retype the last thing that it did and go back and do that exact same problem, only this time with subtraction. So if I want to subtract 3 plus 2i minus 4 minus 3i, there's that same negative 1 plus 5i that we got. And then we also did I times negative 3i. So if we do I times negative 3i, then there's that same positive 3 that we got. So if we switch our calculator from real mode to A plus BI mode, we can type those in the same way that we did them by hand and come up with the same answers. All right, let's look at the next one. For the next one, we have the square root of negative 4 times the square root of negative 16. Now, we know the square root of negative 4 would be the same thing as the square root of negative 1 times 4. And the square root of negative 16 would be the same thing as the square root of negative 1 times 16. So square root of negative 1 is I, and square root of 4 is 2. Over here, square root of negative 1 is I, and square root of 16 is 4. So if we put those together, 2 times 4 is 8, and I times I is I squared. We said that I squared is equal to a negative 1, so that would give us 8 times negative 1, or negative 8. Now, one of the most common mistakes that students make on this problem is typically when we're working with radicals and we're multiplying, we can combine what's underneath the radical. So we typically would be able to say negative 4 times negative 16 is a positive 64, and the square root of 64 is 8. But you'll notice that that rule does not apply here. Because the square root of negative 4 does not truly exist, it's imaginary, it's not real, then the rules that govern real radicals don't apply here. So I want to be very careful that I don't make this mistake. If I have the square root of a negative number, I cannot combine it under the radical with another negative number to get that negative to disappear. I lose my imaginary, and I'm not allowed to do that. All right, next thing we want to look at is something called a complex conjugate. We've used these before, but just for review, if you have something like 3 plus 2i, its complex conjugate would be 3 minus 2i. It's the exact same real a value and the exact same b part of the imaginary number, but the sign in between would be the exact opposite. If I go through and I multiply a complex number by its complex conjugate, I'm going to FOIL just like we normally would. So I'm going to say 3 times 3 is 9. 3 times a negative 2i is a negative 6i. 3 times a positive 2i is a positive 6i. And then 2i times negative 2i is negative 4i squared. The negative 6i and positive 6i will cancel each other out. And of course, I squared is negative 1. So negative 4 times negative 1 would give us positive 4. So 9 plus 4 would give us 13. The best part about this is you'll notice that when you multiply a complex number by its complex conjugate, the imaginary piece goes away. That's going to be important for us in a few minutes. All right, look at the next one. For the next one, we have 3 plus 2i squared. Now, 3 plus 2i squared literally means 3 plus 2i times 3 plus 2i. So again, if I go through and FOIL, I would get 3 times 3 is 9. 3 times 2i is 6i. 3 times 2i is 6i. And 2i times 2i is 4i squared. So if we combine what we can, we could combine the 6i and the 6i to get 12i, and I squared is negative 1. So 4 times negative 1 would give us negative 4. Negative 4 and positive 9 gives us 5, and so there's our answer in standard form, a plus bi. Again, what I don't want to do here is when you see that square, that does not mean square the first number and square the last number. I can't just square the 3 and get 9, square the 2i and get 4i squared. You'll notice that does not give me the right answer. I do have to FOIL that out. So that's another common mistake that students make that we want to be aware of and prevent. All right, what about dividing complex numbers? If I have 1 divided by 1 plus I can't leave it in that form because I is the square root of -1. That would be leaving a radical in the denominator. And when something is in its simplified form, we're not allowed to have radicals in the denominator. So we saw just a moment ago that if you multiply a complex number by its complex conjugate, it makes the imaginary component disappear, right? They cancel each other out. So that's what I want to do. I want to multiply 1 plus I times its complex conjugate, 1 minus I. Now the only way that I can do that is what you do to the denominator, you also do to the numerator. So let's go through and multiply. 1 times 1 minus I would give us 1 minus I. And in the bottom, if we FOIL, 1 times 1 gives us 1. 1 times negative I gives us negative I. 1 times positive I gives us positive I. And I times negative I gives us negative I squared. So the negative I and the positive I will drop each other out. I squared again is -1. So now we have 1 minus -1, which is 1 plus 1. That's 2. So we got rid of the imaginary part. They still want me to write this answer in standard form. And standard form is a plus bi. So I'm going to put the 1 over 2 and I'm going to put 1i over 2. So that would be 1 over 2 minus 1i over 2. And again, I'm going to write that as 1/2 times I so that it's a plus bi. Last thing that we want to look at is how you can graph a complex number. Complex numbers are not real, so you can't graph them on the traditional Cartesian plane. The only way that you can graph an imaginary number is on a complex plane. And the way that someone will know they're looking at a complex plane is it's not labeled X and Y, it's labeled real and imaginary. So we would graph that by graphing our real part, A, and our imaginary B value that typically goes with our I. We're going to graph that like we would an ordered pair. So if I have the number 2 plus 3i, I'm going to pull out, this is A plus BI, I'm going to pull out AB. So I'm going to pull out the 2 and the 3. And because I have this labeled real and imaginary instead of X, Y, now I can plot that just like I would a traditional ordered pair, where I'm going to say my real part is positive 2, so I'll go on the horizontal axis 2. And my imaginary part is 3, so I'll go on the vertical axis 3, and that would be 2 plus 3i. All right, look at the next one. For the next one, we just have 4. All right, if we just have 4, that is 4 plus 0i, right? So that's the ordered pair 4, 0 if we're pulling out A and B. So we could go on the horizontal axis to 4 and then not move off of the vertical axis, and so that would be our graph. Look at the next one. For the next one, we have negative 3i. Negative 3i was 0 minus 3i. So if that was 0 minus 3i, we could write that as the ordered pair 0, negative 3. And then we could graph 0, negative 3. All right, so here is your homework for tonight on pages 180 to 181. We're doing 1 through 73, every other odd, challenge 81B. Pages 180 to 181, 1 through 73, every other odd, challenge 81B.